Hey everybody, Mr. Bells here. This lesson is going to be for my Geometry A class. Again, there's a big ideas math assignment that goes with it for section 3-4. This is all about perpendicular lines. Perpendicular lines are lines that intersect that form 90-degree angles. How we can get them, how they're going to help us with different proofs. I'm going to kind of go through your journal right now with some of this stuff. So if you could have that out, maybe pause the video, make sure that you are looking at that as we go through it. Again, there is a big ideas math assignment that goes with each one of these video lessons. So here we go. Do my best to be able to put these things in here for you. So the first thing that we're going to talk about in our note taking, this is page 83 in the journal, 83 in the journal. What the heck is distance from a point to a line? So anytime you have a point and you have a line someplace, if we're trying to find the distance, I'm going to have all of these different things on here just like this. Well, the distance from a point to an actual line should always be at a 90-degree angle to that line through that point. So when we're talking about that distance, even though I can draw it several different ways, we want the shortest distance possible, shortest. And that shortest distance is always on a perpendicular to that line through that point, okay? You guys know we've already talked about this before, but a perpendicular bisector, say I have a segment right here, AB, and if I want a perpendicular bisector, then I have to have a point C that's in the middle so that that segment and that segment are equal. And then I have to have another, whether it's a segment, array, a line, I don't really care, that goes through that midpoint so that it forms right angles. And I'm going to do a couple constructions again that we've done in class, and I think I've done on some of the other videos too, just to kind of remind you of how to do those perpendicular ones. Okay? So what are some of our new theorems that are coming up in 3-4? And again, theorems are things that we can prove are true based on other stuff that we know. So here we go. This one says theorem 3.1, linear pair perpendicular theorem. Remember, put these, check mark, all of these things in that big pile of knowledge that you're getting for this class. So it says if two lines intersect to form a linear pair of congruent angles, then the lines are perpendicular. Well, what the heck does that mean? So first off, I have to have a linear pair. And if these angles are congruent, which means they're the same, hopefully you know this. If they're a linear pair, then we'll call this angle A and angle B, just to make it easier. Then angle A plus angle B must add up to 180 degrees. Well, if they're congruent to each other, if angle A is congruent to angle B, and that was given to me, right? Then angle A equals angle B, right? That makes sense by definition of congruence. That's the thing that takes us between those congruence and equality symbols. And if two things are equal to each other, then I can take one and substitute it in the other one. So that means 2 of angle B's equal 180 by substitution, right? I can just throw that up there and simplify at the same time. Divide by 2, then angle B must equal 90 degrees. By division property of equality, I divided both sides by 2. And then if angle B equals 90 degrees, I can do substitution again and get angle A equal to 90 degrees. If I wanted to show that they were both there. And if one of them's 90 degrees, then the lines must be perpendicular. That's kind of how we prove that one. Okay? So again, 90-degree angles means right angle, which means perpendicular. So perpendicular transversal theorem, here's another one for you right now. Again, just kind of talking about it. It says in a plane, if a transversal is perpendicular to one of two parallel lines, then it's perpendicular to the other one. So let's do this. So what it says is this, is these two things are parallel, and this line right here is perpendicular to this one. Good deal? So I'm going to say this, just kind of give you a quick little rundown through it. If this is perpendicular, then this angle must be 90 degrees, right? if this angle is 90 degrees, then this angle must be 90 degrees because those are corresponding angles. And the corresponding angles theorem says that if two lines are parallel, then corresponding angles must be congruent. Now I can say if this is 90 degrees, then by definition of perpendicular lines, right? If this is 90 degrees, if two lines form a 90-degree angle, then they must be perpendicular by definition of perpendicular lines. Hey, they're perpendicular, which is what we're trying to prove. Okay, so that's two of them. Again, if these two things are congruent, then and they're a linear pair, then they must be perpendicular. These ones, if these are parallel and it's perpendicular to one of them, it must be perpendicular to the other one. So all of these proofs are really, again, proving perpendicularness. So let's go over here, see if this one makes sense. This one actually doesn't prove perpendicularness. This one proves parallelness, right? The then is the proof that we're going to have. Like that. Hopefully that helps. So this one says this. It says if we got two lines that are both perpendicular to the same line, then those two lines must be parallel. Well, I'll try it again for you, see if this makes sense. If they're perpendicular, then this angle equals 90 degrees. If this is perpendicular, then this angle equals 90 degrees. If both those angles, which are corresponding angles, because they're both in the top right positions, then the lines must be parallel by the corresponding angles theorem. Wait for it. Converse. Remember, the converse of those statements is what proves lines parallel. So that's kind of how that one works. So then you're going to see other stuff in your notes right here. It's going to say, hey, find the distance from point A to BC. So point A is right here, and line BC is right here. So the question is, would we want to use that distance right there, AB? Would we want to use that distance right there, AC? Or would we want to use this distance right here, AD? And I hope, from what I said just a little while ago, finding the distance from a point to a line, we want to always do it on the perpendicular. That's the shortest distance possible. So that means I'm doing the distance from -3, 0 to -1, -2, doing the distance formula. So the distance formula, again, what I need to do is I need to find the square root of the difference between the x's and the difference between the y's after they've been squared. So basically I'm going to ask you this. How far is it mathematically or distance-wise from -3 to -1? And you're going to say that's 2, and we square it. And then how far is it from 0 to -2? And you're going to say it's 2, and we square it. And that goes underneath a big square root. So again, the difference in the x's squared, the difference in the y's squared. Okay? If you put down the distance was negative, don't, right? The negative sign is going to get canceled by the square anyway, so don't put a negative down in here. So 2 squared is 4, and 2 squared is 4, so that is the square root of 8. And I'm wonderfully okay with that. That's what it equals. That is an exact answer. There's no rounding going on there. The problem is a lot of us don't know what the square root of 8 actually is. So I want you to use some common sense and know the square root of 9 is 3, right? And the square root of 4 is 2. So the square root of 8 must be somewhere between 2 and 3, probably closer to 3. On my calculator, I can do this. Second, right over here is the square root button underneath the x squared. Square root of 8, and I hit enter, and I can see I get 2.83 if I round it up. So an approximate answer is 2.83 units. That's the shortest distance from that point to that point. Okay? So then what I'd want you to do is I want you to practice one. So pause the video right now and let's do this one. Go ahead and do that. Again, stop the video. Sweet. Hopefully you did that. I'm going to give you the answer here right now just to make sure that you guys are good and on top of stuff. So I need to go A to D, because that's my perpendicular. So from -3 to 3, that's 6, so 6 squared. From -4 to 2, that's 6 squared also. So that's 36 plus 36 is 72, and I need to square root that. I know the square root of 64 is 8. I know the square root of 81 is 9, and 72 is somewhere between 8 and 9 then. So again, that's an exact, an approximate. I'm going to go ahead here on my calculator again, do 72. I'm going to show you a different way just because this is kind of cool, and it'll lead into some stuff you'll do in an advanced algebra class later. I'm going to raise it to the 0.5 power. Watch. Oh, look at that. So a square root and raising it to the 0.5 power, actually the same mathematical stuff. Same mathematical stuff. Watch, I'll do it the long way. Square root of 72. And you can see same numbers. Same numbers. So if you want to do square roots on your calculators, you can also just raise it to the 0.5. I think you usually end up with less screw-ups when you do that. Okay. So again, that answer was 8.485, or approximately 8.5. Sweet. Let's continue on and see if we can justify any of these things, prove any of these things are stuff using perpendiculars. So it says in exercises 5 through 8, determine which lines, if any, must be parallel. So on this one, can I prove that P and Q are parallel? Dun, 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 dun. What I'm going to say is to look right here. Is there any markings on any of those angles over there? And the answer to me would be no, which means that I could take this line Q and I could tilt it like that, couldn't I? There's nothing that locks that in. So if there's nothing that locks that in, then I cannot assume that P and Q are parallel. It could be off by just a smidge. You see what I'm saying? Okay. So nope, nada, nope. Okay, this one over here. Can I prove any of these lines must be parallel? Again, that's what we're asking for. Must be parallel. Okay, so hopefully you did this and you went, oh, look, that's perpendicular and that's perpendicular. Yeah. So that means P must be parallel to Q. And you're like, well, why? Why? Well, look, right over here. Oh, nope, right up here. The lines perpendicular to a transversal theorem, right there, says if two lines are perpendicular to the same line, then they must be parallel. And these two lines, P and Q, are perpendicular to the same line R, therefore they must be parallel. Now the question is, are S and R parallel also? And you'd be like, no, they're not. Okay, at least I can't prove that they are. Once again, there's no markings on these angles, these 8 angles over here, so that S line is tiltable, so I can't go any more on this. Okay, so let's go over here to this one, number 7. Do you agree that J and K must be parallel? J must be parallel to K. Because you can see if this is 90 degrees and this is 90 degrees, then they're both perpendicular, right angles, whatever. In fact, if there's one 90, then there's all of them that are 90 or perpendicular there. So then I go here, I go, hey, if this angle and this angle are both right angles, right, then M must be parallel to N also. Good deal? Okay, coming over to this one right here, number 8. I'm going to blow that up so you guys can see that better. So here's the first deal. So right here, angle 1 and angle 2 are congruent, right? Angle 1 and angle 2 are congruent. You can see that by the little tick marks. Oh, wait. Do angle 1 and angle 2 form a linear pair? Like, yes. So that means that those must be perpendicular. So if those are perpendicular, then this angle and this angle are both perpendicular to line N, right? So that means that S is parallel to T. And if this angle is, if this is perpendicular, then it's 90 degrees, right? And if this is perpendicular, then it's 90 degrees. And this angle right here and this angle right here are alternate exterior angles. And if they're both 90 degrees, then the alternate exterior angle's converse says that M must be parallel to N. Okay, so hopefully this was beneficial on some of this stuff. This is all about perpendicular lines. So if I go one more page, that's beyond that. So I'm going to finish with a couple of quick little constructions so that anybody who was having issues with constructions before, you can see it again. So step number one, I'm going to do this one. I'm going to do perpendicular bisector of a segment. Perpendicular bisector of a segment. So I'm going to go here, here, A and B. We talked about this. Bisector means it's got to go through the midpoint, right? This is not a midpoint. This is not a midpoint. Someplace right in here is a midpoint. And perpendicular means that it's got to be at a 90-degree angle. So I'm looking for that exact one. So how do I do that? I take my compass like this. I put it at A. I open it up over halfway. I don't care how far it is, but it's got to be over halfway. That's over halfway. And I swing an arc, just like that, all the way through. I come over to B. Notice where I hold my compass and put it right down there low by this. And I kind of tilt it down towards the paper. And I can move the paper or I can swing the arc. Either of those things are going to do that for me. Now the two places where the arcs cross, right there and right there, is what we need to connect. So I'm going to go here and here. And look at that. If I measured this angle right now, which again I'm not allowed to do with a construction, but I can do it to check afterwards. Do you see? Look, it's 90 degrees. So that means that those are perpendicular. And then if I measure this distance right down here on the bottom, measure this distance to the center right here, that looks like it's 1 and 4, 5, 6, 1 and 13/16. And then right over here, oh my gosh, look at that. 1 and 13/16. So that means that those two things are congruent. So that is, again, a perpendicular bisector construction. Perpendicular bisector construction. I'm going to do one more for you right now. I'm going to do perpendicular through a line, 2 points. Okay. So I'm going to go this. I'm going to do a line. I'm going to do it on an angle so it looks a little freakier. And I'm going to put a point right there. And I'm going to say that there is one and only one line that goes through this point, right? That's also perpendicular to this line. Billions of lines go through that point, right? And billions of lines are perpendicular to the green one, but there's only one that's perpendicular and goes through that point. That's what I'm trying to find. So again, this construction called perpendicular to a line through a point. Good deal. And this point could be on the line, it could be off the line. It honestly doesn't really matter. What I'm going to do first, if it's off the line, is I'm going to swing an arc and put the point on there. I'm going to swing an arc so it goes, swing an arc so it goes through my down line, right? Both sides. Now, if I swung this arc and it didn't touch it, like the line wasn't long enough, right? These are lines, so I can simply take that line and extend it as long as I want. It doesn't matter. So I extended it. Now it definitely touches through those things. Yes? Everybody see that? Okay, so now what I'm going to do is from this point and this point, we'll call these A and B, I'm going to swing arcs below the line further. So from B, I swing an arc right there, and from A, I swing an arc right there. Now if I wanted to, I could do those up above, but I'm going to show you something that's kind of cool. Watch what happens. I'm going to go ahead and draw that up. So I believe that this is perpendicular to that line, and it went through that point. But watch what happens. It's kind of magic. I'm going to keep that same opening for those arc swings, and I'm going to move it up there. I'm going to move it up there, and oh my gosh, look at that. The intersection point is exactly at that point also. Or if your compass was bigger and you switched the compass settings at all, it would have just simply intersected someplace on that line that still goes through those points. So hopefully this was really helpful to you. Remember again, this is Geo A, section 3-4, dealing with perpendicular lines and proofs. Make sure you do the homework that's online that goes with it, and we'll see you in class soon. Bye.